Hello wonderful person, this is Anton, and today we're going to be discussing the idea behind the dark energy and what exactly seems to produce it. And specifically, we're actually going to be discussing this somewhat controversial proposition that has now gained even more support in the scientific community in the last few years. And specifically, we're going to discuss the idea behind black holes potentially being the source of this mysterious dark energy. And even though for decades we've treated black holes and dark energy as two completely separate mysteries, some of these recent studies propose that it could be basically two sides of the same coin. And so in this video we're going to discuss this new concept referred to as the cosmologically coupled black hole principle, and some of the recent data from these studies that, if correct, may change our understanding of the universe and how everything works. But to understand all of this, we of course have to discuss black holes and dark energy first, just so that it all makes sense. And that's because normally we think of black holes as these localized monsters that pull all of the matter inside and never let it go, while the mysterious dark energy seems to make up approximately 68% of everything in the universe and seems to push everything apart, but exactly what it is, we actually don't know. And I guess let's start with this first. So what is dark energy? And what do we know about it so far? Well, technically this is going to be a very short explanation, and that's because we don't really know much. But we know that back in the 1998, researchers confirmed that the universe is not just expanding, but it's accelerating its expansion. Or basically it's expanding faster and faster and faster. And what's causing this is now referred to as dark energy. This is what we usually refer to as the lambda CDM model. And here the assumption is that this dark energy is some kind of a cosmological constant, or basically a kind of a fixed amount of energy inherent to the space itself, or it's basically the part of space itself that doesn't seem to change and causes the space to expand just because of some kind of a fundamental property. But as we've discussed in one of the recent videos, the new data from the Dark Energy Spectroscopic Instrument, also referred to as DESI, has recently sent a lot of shockwaves across the scientific community. And that's because, based on the observation of approximately 15 million different galaxies, here the new data suggests that dark energy might not really be a constant and seems to be actually weakening over time. And if it's not a constant, then our standard model of the universe might be in trouble, and the cosmology as we know it requires a completely new explanation. But then we have black holes. And this is actually where this black hole explanation comes in and tries to explain this. Now first, just so that we're clear, we're mostly referring to supermassive black holes in centers of various galaxies, because individual stellar mass black holes are just not massive enough to influence any of this. But based on the research from 2023, and the research we discussed in one of the videos in the description, here Duncan Farah, Kevin Crooker, and the team you see in this list published a study that looked at these supermassive black holes, but mostly in very old elliptical galaxies that are no longer active and have actually been completely inactive for a very long time. Here we're talking about galaxies that resemble something like this, that basically just look like these very large orange blobs. And so here most of the stars are actually ancient, and there's practically no star activity and no black hole activity as well. And so these galaxies are kind of unique because they have very little gas left inside, and thus do not possess the material needed to continuously feed the central black holes, or at least feed them through the traditional accretion process. And that means that we assume that many of these black holes are not really going to be that massive, or at least not as massive as the ones that are active. And so at least according to standard physics, these black holes should not be growing much at all. But when the team examined some of these galaxies, and especially when they looked at some of these galaxies over the span of 7 to 10 billion years, or basically compared 10 billion-year-old galaxies with the ones that are much closer to us, they found something somewhat surprising. The black holes were generally 8 to 20 times more massive than they were in the early universe. And in this case, this growth could not be explained through accretion or just by eating matter, or through the merger process involving colliding galaxies. In other words, their total mass was very difficult to explain. But instead, this mass increase surprisingly directly correlated with the expansion of the universe. Or essentially, as the universe expanded, the black holes seemed to grow as well. And this led to this new concept now referred to as cosmological coupling hypothesis. Or basically a hypothesis that now suggests black holes seem to be coupled with the universe itself. and specifically coupled with the fabric of space-time, suggesting that as the universe expands, so do the black holes. They seem to gain mass automatically, in a very similar fashion to how a photon loses energy as it travels through expanding space, but in this case it's obviously in reverse. And here the strength of this coupling was represented with the letter K. This was basically a new type of a value, and so if K was 0, there was no coupling, which is what technically Einstein predicted, and what most of the modern models of black holes seem to suggest as well. But if K was 3, the black hole grows exactly at the same rate as the volume of the universe, suggesting some kind of a natural connection between the black holes and the expanding universe. And well, when they actually tried to assess this, or basically when they analyzed the data based on years of observations, they did discover the value to be 3, or basically the observational data seemed to almost perfectly fit their prediction. And this was of course significant because it kind of implied a direct connection between this vacuum energy or dark energy and the growth of black holes themselves. Or just to rephrase this, it suggested that black holes could be the source of the acceleration of the universe and could be producing dark energy inside of them. Or at least that was the slightly controversial conclusion from that 2023 study. And the thing is, this was not the only team and not the only study to make a similar proposition. Here's another one from 2025, and it also proposes that black holes seem to act as reservoirs or bubbles of dark energy, and that the increase in dark energy seems to overlap with the increase in black holes. But I guess the big question here is, okay, so how can a black hole actually do any of this? And how can something made out of matter become dark energy? Well, in this case, this hypothesis proposes that inside these black holes, there is really no singularity. And that's actually something that most physicists would agree with, mostly because singularity, or infinity, is usually seen as a kind of a placeholder for something that we actually don't understand. And so nobody actually thinks there's infinite density or even infinite mass inside, and instead it's just something we still haven't solved, and something that needs to be examined. But in this hypothesis, this particular point is now imagined to be some kind of a core of dark energy itself. And so as stars go supernova and as they collapse into black holes, or as massive black holes grow larger and larger, they're essentially converting some of the regular matter, or basically stuff that falls into them, into dark energy itself. And in this case, this kind of solves several issues in cosmology, but obviously creates some new ones. And first, this obviously solves the source of dark energy. It explains where all of this energy is coming from and what's causing the expansion itself. And so here the source is obviously various black holes across the universe. Their collective gravitational energy seems to produce just enough dark energy through some kind of an unknown process. At the same time, based on this 2025 study, this also surprisingly solves the neutrino mass problem. And that's because based on some of the recent DESI observations, it's even been suggested that neutrinos, or these mysterious ghost particles, may even have negative mass. Or at least they would have this negative mass in order to make some of the cosmic math work out. But that's technically impossible. However, according to this study, if black holes are converting matter to dark energy, it actually rebalances some of the cosmic budget and then allows neutrinos to have a normal positive mass that surprisingly matches various experiments. In other words, here it seems to solve another major issue. And last but not least is of course the famous Hubble tension, something we've talked about very recently in one of the videos in the description. And so here it could explain why we seem to have different measurements for the expansion of the universe at different times. And though it's supposed to be constant, it's called the Hubble constant after all, here we know the expansion rate seems to be different, and in this case could be explained because black holes are also changing, and there was even a time when black holes were forming most rapidly, which surprisingly corresponds to the highest value of the expansion. This happened approximately 10 billion years ago. But before we conclude that black holes seem to create dark energy, we obviously have to discuss some of the counter-arguments as well. Because here it's very important to stay grounded, as this is a somewhat controversial idea. And while one major counter-argument is that we might be misunderstanding how black holes grow astrophysically. Or to be more exact, it's quite possible that even in these inactive galaxies or these elliptical galaxies, there could be some hidden ways for black holes to grow larger, possibly through mergers we are not familiar with, or through a process of microaccretion that just has not been accounted for yet. Or just to rephrase this, some of these massive black holes could be growing through additional processes that we just have not discovered yet, which would obviously explain why they appear to be bigger than they should be. Furthermore, there are some mathematical hurdles as well, and that's because for a long time researchers struggled to find a version of Einstein's equations that allowed a black hole to be embedded in an expanding universe without creating mathematical singularities. Or essentially, the math would often break at the edge of the black hole, which is technically what this recent study by Cadoni and colleagues from Italy mostly focused on. They actually found at least one mathematical solution where these black holes could be a part of expanding universe and could remain regular and stable everywhere except at the very center. And so here this work shows that by including the expansion of the universe with what's happening on the surface of the black hole, or basically at the event horizon, some of these mathematical problems seem to disappear, which technically does present us with at least one possible proof for black holes being the source of dark energy. But I guess the question is, okay, so why is this important, and what exactly does this teach us? Well, if this hypothesis holds up, it basically means that dark energy, or this phenomenon we still don't really understand, seems to be an astrophysical phenomenon created by the life and even death of stars themselves. And it's not just some kind of a mysterious vacuum energy, and not some kind of a property of empty space. It is actually something physical and something that's constantly generated. And more importantly here, this would directly connect centers of galaxies, and of course centers of various black holes that used to be stars, with the extremely large scale of the universe, where everything basically seems to be expanding. And so I guess here this might actually suggest that the universe's expansion is directly tied to star formation, or technically star explosion. And since star formation was at its peak during the so-called cosmic dawn, or basically the peak was billions of years ago and is now slowing down, it also suggests that the growth of dark energy should be slowing down as well. And well, that's exactly what the observations from DESI seem to suggest. In other words, it might explain why the acceleration of the universe seems to be slowly decreasing. But right now this is just one of many different explanations for what we're seeing here, and at this point this is still just a hypothesis and does not have that much support. But we are definitely at the point where some of the models have to change now, mostly because the new observational data challenges everything we knew so far. And so whether the source of dark energy is black holes or something else entirely is still being actively debated and will be debated for many years. But based on these recent studies, the evidence from these elliptical galaxies and the masses of neutrinos is definitely just a little bit compelling. And luckily for us, we'll definitely have more data coming from the Euclid telescope and even DESI right here, that in the next few years will help us determine what's happening here. And so for all we know, maybe it's just a coincidence, or for all we know, maybe it is black holes after all. On that note, we'll definitely come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.